I think the official title of the talk was Robust Deep Learning under Distribution Shift, but I have a predilection for one line. Avoiding line breaks when possible in slides, so don't be alarmed. So I'm going to talk about the work that started with so there we go. So maybe to tie this into some of the broader themes that have come up the last couple of days, I guess I started at some point trying to figure out what people were talking about when they were writing all these interpretability papers. It's just a young machine learning person doing supervised learning like anyone else. And it seemed like there was a weird combination of people had a lot of valid concerns about cases where doing prediction alone is a problem. And at the same time, a menu of solutions that wasn't clear if it addressed any, let alone all of those problems. And then maybe started trying to go down the rabbit hole of some of those concerns, whether they were estimating causal effects or sort of external validity, somehow generalizing to a different distribution. This is actually, I guess distribution shift or domain adaptation is a bit of a gateway drug to causality. So warnings to anyone who starts thinking about it. Eventually you'll have to ask why the distribution shift, and then you'll find that your familiar assumptions map onto causal assumptions. So this work spans a few papers. It started with this paper together with Yixiang Wang and Alex Smola on detecting and correcting for label shift, which is a pretty classical kind of rigid assumption, but where we could say concrete things. Expanded into the empirical. And I'll kind of talk about a couple follow-ups here. One about just detecting shift generally. One about how we correct for it and whether the techniques that are like familiar toolbox for correcting for shifting distributions are still valid in the context of deep learning. And finally, I'll talk about a recent paper. This is not actually the title of the paper, but maybe it communicates a relevant take-home about a recent family of methods called Domain-Adversarial approaches that are intended to correct for distribution shift, but do so under unstated and often violated assumptions. So this work is with a bunch of collaborators. When making this slide, I was kind of reminded of the stark gender imbalance in the field and my maybe failure to do more. So there should be a 1 in 256 chance of this happening, and hopefully never again. Basically, the high-level problem here is supervised learning setup. Says some process, let's just say God, makes lots of data fall out of the sky, and we use it to train a model. And now that model has, the ML algorithm has produced a function, and we're going to apply it in the future on more data that hopefully also falls out of the sky, but from like a copy-pasted God that has had no change of opinion in the intervening period. And then, basically, if we did good on held out representatives from the source distribution, we should do well at test time in the target distribution. And the reality is just, the real world's complicated and we have no idea what's going on. But there's many manifestations of different kinds of real world mechanisms that give rise to this difference between the data we see at train time and in the desired deployment setting. Some of them kind of benign, some of them where we have some kind of, must do some introspection about our sort of moral role in this world, and some of them, somewhere in between. So, you've heard a lot about adversarial examples. I won't spend too much time talking about them. That's one case where we've basically assumed that up to some changes within a small neighborhood, the new distribution and the old distribution are basically the same, and that the process for creating the new data is you sample a point from the old distribution and then move it within a little ball. Perhaps most of the attention is on adversarial examples, rightly, sort of because it's intriguing for the very reason that we're intrigued broadly by the perceptive qualities of capacity of convolutional neural networks and this new ability. But perhaps maybe the most common like real-world adversarial attack that people have been dealing with for a long time is people trying to get by spam filters. So you want to keep the message more or less the same. You want to keep the email qualitatively similar, but you want to monkey with the spelling to bypass whether it's bag of words, keyword filters, whatever it is. So a recent paper at ACL here. I won't go into the details, but basically it turns out if you take, say, a sentiment classifier, you can, based on state-of-the-art techniques like fine-tuning, giant BERT, sort of fill-in-the-blank language model type thing to your downstream task, you can cripple the model, basically bringing it down from 90% accuracy to worse than random guessing by just altering one character. So it's not a phenomena specific to images, but there's also problems in text. Text is a little bit funkier because there's no such thing as an imperceptual change unless it's like you've got a font where lowercase l's and uppercase i's look the same. Another kind of failure mode is that we don't actually have training data from even the realistic deployment setting. So things like reading comprehension or question answering, a lot of times what we're doing is we're creating synthetic data sets that we hope are somehow related to the downstream task, and we're going to put them out there. And in a paper at EMNLP last year with one student, we showed that basically so this is a task, they call it reading comprehension just to make you question what comprehension means at all and force you to develop new vocabulary. It's really just question answering. The inputs consist of a passage and a question. The output consists of some. Often, there's many ways of setting it up. Sometimes it's multi-class prediction. Very often, it's a span in the passage, which is the answer to the question. These data sets are often created programmatically in a way that people think somehow is close enough to the task that if you could solve it, you're really doing something like reading comprehension. Or they're created by being crowdsourced. It turns out that there is enough weaknesses in the sort of data synthesis pipelines that there's all these papers out there basically claiming that they've made serious progress on this problem. They propose a deep neural network. It does this. It looks at the question, looks at the answer, jointly aligns them, non-jointly aligns them, and puts them back together. It stirs them around, and then eventually, uses the fact that it's really read the question in the passage to make an answer. And it turns out that if you take a lot of those very same models and you replace the question with a random question that was not in any way correlated with this particular instance or the label, they get the same accuracy. So if you're not solving the task you think you are, it's another way things go wrong. Sometimes we are the agents of change, and I think this is something we're thinking about more often, is that kind of insidiously, we deploy machine learning where the sort of validity of the system is based on the representativeness of historical data, where that historical data is something like user behavior, and then we deploy it in a context whose very purpose is behavior modification. Surprisingly, things get weird. So on the other hand, you might think, let's just come up with one model that's robust to everything. So let's just find the D model, and that sounds appealing. And there may be certain assumptions under which you can do it, but you can't in general. Like domain adaptation is, I think this is something that, if there's a criticism of, I say this maybe as a self-identifying deep learning person, there's a criticism of us from maybe more quarters like this, it's often that we are plowing into areas not really aware of things that are just already known. In this case, I'm staring at Shai Ben David, who is intimately familiar with impossibilities concerning domain adaptation. But we have a lot of papers that say we solve domain adaptation. We purport to solve it or even address it. But defined only just the source and target distribution are different from each other, that's just an ill-specified problem. It's impossible. And you could just come up with cases where the right answer truly is different depending on what assumption you make. So I kind of wish I didn't put that GIF there because it's giving me anxiety right now. Basically, no classifier will work well in all distributions. You can guarantee performance with strong assumptions, and that'll be like the first part of this talk. Typical assumptions are things like bounded divergence between the source and target distribution by some measure. Others is like assumed invariances, so you assume some kind of invariance class. One common thing is assume invariance on one of the conditional distributions, so either probability of y given x, like the labeling function doesn't change, or probability of x given y doesn't change. That's the assumption that I'll talk about a bit today. It's the anti-causal assumption, or the class conditionals don't change. But it's just worth noting, when x doesn't cause y, so say when y causes x, and if you don't assume realizability, which is a case where sort of both covariate shift and label shift do hold, then the labeling function actually does change. So you truly don't have one model that is the robust model, because the right prediction at source time and target time is different. So if I see someone who has a cough today, I do not think they are a zombie. Fair? But if the zombie apocalypse happens tomorrow and I find out that, it turns out zombie, which is normally very rare, but now is 80% of the population, and one of the early symptoms is cough, my probability that they are a zombie has gone up, only just because the prevalence of zombieitis has changed. Inflammation of the zombie. There. Okay, so the first part we'll talk about detecting and correcting for label shift. So here's the thought experiment. I didn't know anything about this field. I was just kind of starting to think about these problems, and I had this kind of motivation. It was sort of, I train a classifier, and say I'm looking at X-rays predicting pneumonia, and this is going to be not a very realistic example, just kind of motivation. Is that it tells it's a rare disease. Most people don't have it. I'm trying to predict it based on just looking at randomly sampled X-rays, chest X-rays, say. I run a classifier in the training data, and more or less, it's not totally accurate for everyone, but it predicts roughly, the right percentage of people have pneumonia. I run on validation data. It seems that it's also kind of in line with what I expect to see. I run it in the wild, and this is still August when I trained it. And it's giving me estimating roughly the same fraction of people seem to have pneumonia, and I feel pretty good. And then, some period of time goes by. This is just what Google thinks an epidemic looks like. This is not a pneumonia patient. I think it's an Ebola victim. But I run the classifier in the wild at some point in the future, and now suddenly the classifier tells me 5% of people have pneumonia. And so on one hand, you could just think this is great. I train this thing for purposes of doing some kind of public health monitoring or quantification, and now it's told me that the fraction of labels has changed. On the other hand, this tells me the distribution of outputs to my classifier has changed. This means the distribution of inputs to my classifier has changed. Why should I believe anything? In fact, if I went out, instead of feeding in chest X-rays, I fed in cats, would it tell me that 0.05%, would it say there's no change in the rate of pneumonia? No. And my experience this is purely not a mathematical insight, but a deep learning elbow grease insight, is I suspect, and I have evidence for this on a different slide, when I do this, I suspect either 0% or 100% of people will have pneumonia when I feed it to cats. There is no valid answer. Cats neither have nor don't have human pneumonia or something. Another way of motivating thinking about label shift is just that we have this funky way of doing things, which is we train classifiers, say image classification, and a typical thing to do is just go out and collect data with a uniform label distribution, train a classifier, deploy it in the wild. And you can wind up in a weird situation, you get some accuracy, but then you deploy it in a wild with some randomly chosen, not randomly chosen, but it's whatever is natural in the world label distribution, and you sort of, let's say you had balanced errors, you had all your off diagonals in the confusion matrix were equal. You deploy in the wild, you're still going to get 70% accuracy. But you've suddenly, once you encounter a non-uniform label distribution, the problem's gotten much easier. Maybe it's 80% cats out there, and you're still getting 70% accuracy. And so the question is, can we, the high level motivation is basically, can we detect that there's a shift? Can we estimate precisely what it is? Under what assumptions? And can we use this information to recover a better classifier on the fly without actually getting new labels? Humans actually can do this, and I feel a little bit embarrassed that I sent an email to a bunch of friends I knew who were cognitive scientists, so I figured would be able to give me this evidence of humans kind of without any additional supervision, just updating to statistics of some task they were solving, and they pointed me to an ICML paper. These are a bunch of psychologists. So I probably should have done a better lit review on my own before I bothered them. But basically, there's a nice paper from 2010 at ICML called, this is what it's called. I don't have to read it out loud, I guess. And they describe what they call the test item effect. And then basically the idea is they train people on these like very artificial tasks. They're like, they give them some number of training examples. They say these are weebles, these are squeebles or something. Can you differentiate weebles from squeebles? But what then they do is they randomly choose people to show them test sets with different distributions. And what we're able to show is that basically by varying the statistics of the test set, you can cause people to classify, basically the same person shown different fractions of weebles versus squeebles at test time will sort of update their prior and will classify like the same image as a weeble versus squeeble, perhaps, get under some amount of uncertainty, because it's like that thing of like you recognize you're going through the test and you realize, hey, actually I noticed that the multiple choice answers are not actually uniform. There's more D's. And now that I know there's more D's, if I previously would have been equivocal between two answers, maybe now I actually know. I'm more inclined to guess it's D. So the formal set of domain adaptation is we've got a source distribution. We're going to call him P. We're going to call our target distribution Q. I've already been doing that without introducing it, but hopefully I think it wasn't that confusing. And the typical setup here in this, some people sometimes call the standard domain adaptation problem. Some people call it unsupervised domain adaptation. I'm assuming I have labeled data from the source distribution, unlabeled data from the target distribution. My goal is to predict it well on the the target distribution at test time without seeing, when I say well, I mean sort of to do better than I would have if I didn't look at the unlabeled test data, or at least in the setting of shift to do better. But only using the only additional information I have is this unlabeled input data from the target distribution. And I have to do this again without seeing any actual labels. So our goal: detect that a shift has occurred, estimate the new label distribution, correct the classifier. And again, just a reminder from our pneumonia example that if the distribution of our classifier's outputs change, that's enough to already tell us something has changed. So this problem is again in general impossible, right? But there are certain restrictive assumptions that make it quite possible. And one is label shift. So this is what this paper is initially about. And what we're going to assume is the only thing that changes is the label marginal. So we're assuming a generative process where basically y causes x, or we don't have to be assuming it, but this is a natural consequence of the setting where y causes x, which is appropriate in cases like diagnosis because you're trying to predict the cause from the symptoms, which is different from, as we'll get to, covariate shift. So we call this the anti-cause, this sort of, maybe I'm being slightly lying here. So it's not that makes the anti-causal assumption, but it's implied by the anti-causal assumption. And essentially what we're saying is that, this is how the distribution factorizes, where we could just carry over the class conditional distribution from source time. And there's a nice paper that kind of works through by Bernard Cholkoff called On Causal and Anti-Causal Learning that just walks through kind of gently a bunch of different assumptions about distribution shift and what are the corresponding causal assumptions that would have led you to assume that kind of invariance about the conditional probabilities. Contrast this with covariate shift, which makes the opposite assumption. It's this sort of, I sample an x, but then given x, the probability of y given x is what's unchanged over time. And that's the case, I think, that is often, it still might be not given enough, like they might not be assuming shared support, and so it still might be underspecified, but I think this kind of case, this assumption is sort of implicit in a lot of, say, like the adversarial type things, where we're basically assuming that there's a true labeling function and that it doesn't change. Like the same image at source time and target time should map to the same label if you just knew the right function. So it's worth thinking about that we maybe overfit some of our insights to deterministic classification problems, overfit realizability and overfit maybe even the way we talk about, the way we teach prediction is we often say is a labeling function, which sort of, it's almost like described as a structural model where y is given rise to by x versus, you can also still predict y even if x was produced as a consequence of y versus, the opposite. Right, so now covariate shift is appealing in some ways because, well, you know, in the domain adaptation setting, you have samples of the input from source and target. So it's sort of appealing to think that the likelihood ratio that I would know how to estimate is Q of x over P of x because I have samples from Q of x and from P of x. But the problem is just that that doesn't help us when that's the wrong assumption. So if you're in the label shift assumption, you apply a covariate shift correction, that doesn't help you. So the idea here is we're just going to introduce a very simple consistent estimator for the test set label distribution. It's one nice thing about it is it's going to exploit the fact that we have good black box predictors already, and all we need is like a good predictor on the training distribution under the label shift assumption to be able to accurately estimate the label distribution on the test set. We're going to use the black box predictor intuitively at a high level for dimensionality reduction. We're going to use it to get away from ever having to think in, and this is sort of motivated by, I'm a practitioner, so I'm not just thinking like, hey, there's X and there's Y, they're sort of fundamentally the same kind of object. I'm motivated by the kind of case where X is image, and so it's 120,000 dimensions or higher, and Y is something usually comparatively simple, like a classification. In this case, we're thinking about multi-class classification. Our classifier doesn't have to be calibrated, it doesn't have to be unbiased, but the better our classifier is, the tighter our bound on the estimate of the test set label distribution. But regardless, you know, as long as our classifier is not degenerate, and by which I mean it doesn't have a degenerate confusion matrix on the train or test, it doesn't matter, it's the same condition, then we will be able to get a consistent estimator. So as long as we have enough labeled training data and unlabeled test data. So the assumptions are just one, the label shift assumption, class conditional is the same. Two, we need an identifiability assumption. Like we can't recognize labels we've never seen before. So every label we're going to see at test time has to be a label we've already seen at target time, at source time. And we're assuming, this is just the assumption I said before, we're assuming we have access to a classifier whose expected confusion matrix is invertible. And the idea is really simple. We're just going to look at the expected confusion matrices of the same classifier on the source and the target data. And these are different objects from each other. However, they're only different actually because once I fix the class, you know, the distribution of outputs of our classifier is a function of, you know, given y, which and probability of x given y is the same in source and target. So basically the only difference between these two confusion matrices is that the columns are scaled differently. So if I look at the column normalized confusion matrices, so this is like given that y is a particular label, you know, what fraction of the times does a classifier output, you know, each of the classes. And it's easiest to think of it that way. Actually, this doesn't even have to be the classifier output. This could be the softmax outputs of the classifier. It could be any, if we have k labels, it could be any k-dimensional function. But it makes sense that if I just pick the random representation in the classifier, it's not necessarily obvious to me that the classifier is going to learn something such that this matrix would be invertible if I break it down this way. However, it's clear that it should be if this is the confusion matrix, because basically, you know, your classifier doesn't even have to be that good for the confusion matrix to be sort of diagonally dominated, right? You just have to predict when it's class I, you predict I slightly more than the other classes. Like you can still be pretty inaccurate and have an invertible confusion matrix. So on the source data, I can use source data because this guy's the same for source and target. I can use the source data to estimate this confusion matrix. The test data, I can't break it down by column. I can just average them all. I can just say what's the mean prediction. And then I just put these guys together, and it's really simple. I have a linear system, and the solution to the linear system is actually the quantity that I'm after. It is the test set label distribution. And now the only tricky part is that the quality of this recovery is going to depend on how well I estimate the confusion matrix. It's going to depend on how well I estimate this mean vector. And it's also going to depend on the quality of my classifier, because I have to invert this matrix to solve the linear system. And so basically, this is going to depend on the smallest eigenvalue of the confusion matrix. And that's going to be I guess maybe what's interesting there is just that this is a different notion of accuracy than I'm used to thinking about when I say I want a good classifier. Like I can have a very accurate classifier that has two identical columns in the confusion matrix for rare classes, but otherwise does a knockout job on the rest of them. So you could just imagine this would happen if I was looking at the actual confusion matrix, like the hard thresholded confusion matrix for a deterministic classifier, and two of my classes were kind of rare. And so the models never puts them as the argmax, even if it's kind of discriminative. This is one reason why maybe working with the softmax is a little bit more reliable than working with the hard labels. So, right, we just solved this problem. If you go back to working with like the original confusion matrix, not the column normalized, you have the same thing. It's just that what you're solving for now isn't Q of y, but it's actually Q of y divided by P of y. It's the vector of importance weights. So, consistent in that basically this guy's an average is going to converge to its mean. This is also the mean classifier output on the target data is also going to converge to its mean. You can prove that basically as n grows large, if the expected confusion matrix is invertible, the empirical confusion matrix will also be invertible. And you get this simple error bound. Basically says a few things. One, we have this sort of inverse quadratic dependency on the condition number of the expected confusion matrix. We're going to have a sort of irreducible error that's determined either by the number of examples we have to estimate the confusion matrix, the number of training examples, or the number of target distribution test examples. And we're also going to depend upon the norm of the vector of importance weights. So what that sort of tells you is that I think this maybe is an obvious thing actually, but maybe it gives a nice formal way of saying that maybe what we're doing in the first place of saying I'm going to construct data sets that have a uniform distribution over the labels is actually a good idea. It basically controls this term. It's saying, hey, if I have a very rare label at train time, I'm increasing my error in figuring out what the target time, the test time label distribution is. So I can just use a uniform label distribution at train time. But instead of just using that classifier directly, I can use that classifier at target time to figure out what the target label distribution is, and then go back and correct my classifier. But as long as my label data comes from, having a uniform label distribution on the labeled data puts me in the best position to do this recovery, and then I can do the adjustment subsequently.
Sorry, question.
Yeah?
Just to get some intuition, in the case that distribution shift did not even occur, like P equals Q, how do you interpret this result?
Look, you're going to estimate the test set label distribution, and you're going to estimate it imperfectly, and how imperfectly depends on the number of samples you have. If you're going to sort of entertain the idea that the label, if P equals Q, you're still going to estimate it correctly plus or minus epsilon, and if that might mean that you do slightly worse than if you just assume there's no shift. A sort of corrective for that is if you kind of have a prior belief that there's a good chance the distribution doesn't change at all, but then I just want to be guarded against the worst case scenario. I want my default to be to not change. You could just set some tolerance. That's a hack, but you could just say, hey, unless I estimate that there's a significant difference, my default is not actually act upon this. I'm only going to correct my classifier if I think there's a significant discrepancy, and that would cover you. So that way, basically, you'd only be making a change if I were, 1 minus delta sure that there was.
If I understand, the short answer is that this is a worst case bound.
Yeah.
In the case that you have some very rare class that becomes prevalent or something like that, and it may be loose for the easy case of P equals Q.
Exactly. Sure. Thank you. So we can use this also for detection. When you look at the matrix, you realize, well, if this guy's invertible, then basically the test set label distribution is going to change if and only under the label shift assumption. We're still working on the label shift assumption, right? But if that holds, then the label distribution changes if and only if the mean classifier output changes. And so we could just look to the mean classifier output as now, it's sufficient if we assume label shift to detect distribution shift just by looking at the classifier outputs. And this is important because it turns out two-sample testing, there's a nice result by Aditya Ramdas who knows the area so much better than I do. Basically, two-sample testing is easy in low dimensions and hard in very high dimensions. And so now we get to say I'm going to use my classifier output as the object upon which I'm going to test for distribution shift. So, you know, if the classifier output is just like the hard thresholded output, I could just basically I can just do a likelihood ratio test. It's like the right thing to do. In practice, we found when we use the softmax outputs of the classifier as the columns of our confusion matrix, that's like the mean softmax output for each condition on each class, then what we could do is just we could look at the like per component and do a KS test and then use some kind of correction. And so basically we just find that when there's no shift, our type 1 error is controlled. The greater the shift, the more powerful our test, not surprising. We also look at using classifiers of various strengths that have been trained to different degrees. The better the classifier gets, the more power we have for detecting shift, which should not be surprising. If the classifier at 100% accuracy, then we should be in good shape. Here's our estimation errors. This is compared to previous approaches. One nice thing is basically, so the previous approaches were sort of adapted kind of like kernel mean matching to the label shift scenario. And problem there is, when we're dealing with something like images, we wind up with kind of a irreducible error because we just don't have a great similarity function. But our estimator here is actually a consistent estimator. And the more examples we get, we just head towards 0 in terms of estimating the test set label distribution. It's worth noting that maybe there's like a temporal bias, that if I were developing the method 10 years ago or 20 years ago, I might be more concerned about like the 1 to 2,000 example range and think that my method was worse. And the fact that we like cross over at somewhere between 2,000, 4,000 examples is more significant in a world where we typically have more than that amount of data. Now we can apply. So what we've done here, this is kind of a weird plot. I only realized after I created it and published a paper that this is a weird plot to people, is that what we have are two different types of simulated shift. And as you go to the right, the shift is getting greater. And you'll notice our method is, and we're using a kind of weak classifier. If you use a perfect classifier and you're doing image classification, it doesn't matter. You're going to be perfect always. It doesn't matter if you have more cats or more dogs. So we're using a multi-layer perceptron for image classification. People always say, why are you doing better as the shift gets worse? The reason why we're doing better as the shift gets worse is because we're going from a uniform distribution towards something that's dominated by one class. In this case, we're doing it by just making one class, and we're averaging over all the possible classes, making one class more common and rescaling the others. Here we're doing it by basically sampling the label distribution from a Dirichlet, where this is like the concentration parameter, and showing confidence over multiple runs. So basically, as the concentration parameter of the Dirichlet gets really small, it's also dominated by just one class. So it's an easy problem. Like if you go all the way out to the right, the blind classifier gets 100% accuracy. Yeah?
So for the left-hand plot, when you say you, are you doing the shift in training and testing, or only in training, or only in testing?
Okay, so I left out a detail. Thank you. We train the classifier. We use the classifier together with the unlabeled data to estimate the test set label marginal. Once we know the label marginal, the question is, how do you use that to make your classifier better? How are we getting a better classifier? And I was trying to trim slides to fit in more material, but I somehow left out the details. This is really important. There's two things you could do. If you believe that you truly, if you really think that you have a model that's giving you predictive probabilities, there's a plug-in correction, right? Like there's a simple, I'm just going to take my predictive distribution, reweight every answer by the likelihood ratio, and then rescale. That's the right thing to do. The question is, does a neural network, which is what you're using in the first place, give you give you probabilities. Do you believe it? Do you believe that they give you, anything like a calibrated probability? And as we'll see soon, there's reason to believe no. And in that case, what do you do? Well, what we did in this case, we did is importance-weighted risk minimization. So we went back, reweighted the examples, and retrained. And where we'll get to in just a second, if I can actually get that far, is there's a question then of what, if anything, is the role of importance-weighted risk minimization when you're training a deep neural network. And I think Misha's smiling because he knows interpolation will give you the same answer regardless of how you weight the examples, right? If you're truly interpolating. The next step that we did is we looked through this and said, actually, this gives us kind of a general pipeline for detecting shift, right? Because what we did is, it turned out we said, hey, we have a great representation for detecting shift under the label shift assumption, which is just a classifier output. So it was very low dimensional representation, which is sufficient for detecting shift. We just need to detect shift in this 10-dimensional object, not in this 3,000 dimensional object. And then we're just going to do the appropriate 2-sample test. And then the question that we had thereafter was, okay, let's say that cats became more common in the real world. It's never going to be the case. So basically, we have a nice kind of result here that's only nice in a world that you just do not live in, right? So to be kind of humble about the applicability, the class can, if cats became, went from being 20% of photos to 80% of photos, there's multiple subspecies of cat. And they're completely unrelated to each other. There's no way that they all increased in prevalence at the exact same rate. And you went from this number of Siamese cats and this number of Persian cats to they stayed in exactly the same proportions and increased together. The class conditionals do not stay the same. People talk about more sports now than they did a week ago if you're looking at classifying topics. But now they're talking about something else. Last week they were talking about Women's World Cup. And I don't know, maybe somewhere in the interim they were talking about Wimbledon. So the question though is, okay, so if the labels, if the label distribution changes and the class conditional distribution is truly fixed, we have a good detector. And the question is, well, let's say the class conditionals don't stay the same. Now we know an adversary could design a distribution where our method's going to fail. Because you just come up with, you find, you're doing dimensionality reduction. You find any 2 inputs that map onto the same output and just shift mass among them. Now we're just screwed. We can't detect that this shift has happened. But the question is, what are the odds if someone's not being adversarial that they will choose that we have this thing that detects shift, in this particular scenario? Are they, unless they're being adversarial, what are the odds they're going to find the distribution, the new distribution that truly makes our classifier give the exact same distribution of outputs? And so we tried, this is an empirical study, so I make no claims that this is telling you this is always a good idea, no claims about how difficult it is for an adversary, just we look at lots of different things. So we basically look at this general recipe and we say, let's do our thing, which is basically take the source distribution classifier, train it, use the softmax outputs as our distribution for detecting shift. Alternatively, let's use the hard thresholded outputs of our classifier. But we also look at no reduction, so we just look at the input features, which gives us that's just as one baseline. It gives us a tricky, aggregation problem where we have to do some conservative correction, like a massive Bonferroni correction to lose a lot of statistical power. We look at what if we did PCA, what if we do sparse random projections, what if we use an untrained autoencoder, what if we use a trained autoencoder, just get a general feeling. And then another baseline is sort of what would the machine learning person who doesn't really know about 2-sample testing do? And that might be they would just train a discriminative classifier to try to tell the 2 distributions apart. And the interesting answer is it seems that across a whole wide range of different shifts, this is, the paper has specific results. I don't even know if it's meaningful to look at aggregate, but this is an aggregate plot across many, many different types of shifts, whether it's adversarial examples, rotations, just a large empirical study. It seems across the board, and this is with the number of examples that we have to use for detecting shift, we get better accuracy actually using our training set classifier as our representation for trying to detect shift than all of these other things. On non-adversarial perturbations, that seems to in general be the case. One interesting thing is that on adversarial perturbations, And this is just adversarial perturbations like created by the one-step like fast gradient method or whatever. Here, strangely, the thing that detects the shift right away is often looking at the original input pixels. Like just doing KL tests on the input pixels can detect it really quickly, although I'm sure an even smarter adversary could just come up with a way of maintaining the pixel marginals or something. This is the same test applied. Ludwig pointed out, so we ran it yesterday on Ludwig 10 versus CFAR 10. He pointed out rightly that no test that uses a convolutional neural network at all, since the entire methodology owes somewhat to the CFAR data set, could be with absolute unimpeachable integrity be claimed to detect a shift on CFAR 10, because maybe everything is fit to the actual CFAR 10 training and test sets. I won't go to war with him on that. I see the point. But anyway, you see with about 100 examples, you're able to detect there's a shift. And by comparison, this is what you would get if you're training a classifier to just try to predict it. By the way, a classifier gets about 55, 56% accuracy at detecting Ludwig 10 versus CFAR 10. Or I should maybe also say Becca 10 or Ben 10. You get the idea. So I'll just try to hustle through. I think we're getting close. What do I have, like 5 minutes or something? Okay. So one problem is we corrected for the shift by using importance weighting. The question is, what, if anything, is the role of importance weighting in combination with deep learning? So we have a body of literature that makes clear that importance weighting is a good idea when we have model misspecification and like high model bias. So like we have something like a linear model, it's misspecified, and we say, well, if we know that we only have to look at like this region of the input data, we reweight to say only this half is important, then we're going to get out a different predictor. But what got me thinking was I saw Nati give a talk on his work with Daniel in Israel a little while ago, maybe a year and a half ago, or a year ago. And they described this work, and it's analyzing linear networks and extended to deep linear networks and convolutional linear networks. But in all these cases, they say, what is the implicit bias of SGD? What is the separator that it finds on separable data? And what they find is that SGD leads to a solution that is based it's a hard margin SVM solution, and you get something slightly different as you change the architecture. But what bothered me about it is this solution doesn't care what the importance weights are. It doesn't care if we oversample from one of the classes. And so if we go to deep neural networks, for which all data sets, at least these image data sets, are all the training sets are all separable, then what, if anything, are we doing by putting in importance weighting? Because I have these results from my paper that I've published that say that we get a big advantage. And now I'm questioning my sanity, and I want to know basically why does importance weighting matter? Because once you fit everything perfectly, and then all I have to do is blow up the norm of my output weights, I get arbitrarily close to zero error. It doesn't matter what the importance weights are. I could change the importance weight. I could push all of them to zero with the same classifier. So I could look at a 2D example. And so this is with no importance weights. And this is, the red line is like a linear separator, and then the colored lines are just brute force plotting the decision boundary of a neural network. And over time, basically, the neural network and the linear model give you basically the exact same decision boundary. If I change the importance weights, and I look at what happens over time, what happens is here I'm upweighting the blue points. I have a big effect early in training that basically is going to move out. And by the time I get to like epoch 10,000, it's very similar to the original decision boundary. And same the other way, if I upweight the green points. So it seems that I do have an impact of importance weighting. This is a way of somehow altering the optimization by incorporating, but only modulo the early stopping criteria. So I've expressed now how much I'm correcting for distribution shift, or what I think I'm doing, in terms of like the wrong abstraction. Now I'm tuning the early stopping knob to try to impose my prior, which just seems like I don't know what is the correct level of early stopping. Now this is not 2D data, but CFAR data. So I look and say, basically, I'm going to try weights all the way from like 512 to 1 one direction, 512 to 1 the other direction. And I'm basically going to look at, over epochs of training, what fraction of images are classified as dogs versus cats. This is dog versus cat CFAR, just two-class CFAR binary classification. You see, early in training, there's a huge effect that disappears, and over time, like these guys are not even in the order of the importance weights. This is just because of like random runs. So basically what happens is I have a big effect that tapers off towards nothing, and basically up to like importance weightings of 256 to 1, which is probably bigger than you'd normally want to use just because you're reducing your effective sample size. You'll eventually converge to like the same exact decision qualitatively. I'm not saying it's the exact, I can't visualize 3,000 dimensional loss surface or whatever, but you're getting qualitatively in that these models are basically, if we look at fraction of, this is at epoch 1,000, after 1,000 epochs, we look at fraction of cats that are classified as dogs. It's the same across the importance weights. Something funky happens at like 512 or 256 sometimes and it blows up, but other than that. Fraction of dogs that are classified as dogs is level. Also, of random vectors, just truly random vectors, like uniformly sampled in input space, they are all cats. This is just like a weird thing that happens, but there's no right answer, right? If you say the model's constrained to say it's got a probability, it's the sum of the probability it's a cat and the probability it's a dog has to be 1, and if it's neither, the model's sort of just fundamentally, semantically incoherent. Interestingly, I think this is motivated by the intuition from Nati and Daniel's paper. It said that the conversion to this sort of weight agnostic solution is related to the norm of the weights blowing up. We looked at what happens if you use L2 regularization. L2 regularization does change the decision boundary. You get a different decision boundary when you use importance weighting if you have L2 regularization. However, now I have another knob that's also sort of the wrong knob. So the final thing to say here, importance weighting can affect deep learning, but only via like kind of the wrong abstractions, and I have no guidance for what's the right way to choose them. So this is like a serious problem. It might even be, I think a conventional wisdom for a long time has been don't downsample your data, weight it. And it's possible maybe that you actually should downsample your data. I don't know, I have to think it through. And finally, we looked at domain-adversarial networks, and I think I'm out of time, so I'm gonna end here. But basically, I think this is a cautionary tale of what happens if we're not, we could be very precise about under what assumptions we develop a model that's correct, and then we could even try that model in cases where the assumption doesn't hold and be clear about that. But there's a whole industry, thousands of citations, a whole almost subfield of people reviewing the same subfield's papers who are saying the way to deal with domain adaptation is you make a representation such that the source data and target look the same in representation space. There's a problem with that, which is that the easy counterexample is precisely what we've been talking about the whole talk. It's label shift. If the label distribution is different and you make them look identical in representation space, and you're applying the same predictor on top of that representation, you're lower bounding your error. You're basically saying if I had 75% and 25% and it flips to 25-75, then by forcing them to look the same in representation space, I'm actually going to say I have to get at least like 50% error. So this is a big problem, and there's a theorem that's Shai is invoked as the like, this is the right thing to do because there's a bound on the target error that depends on 3 terms, and we minimize 2 of them. The problem is they minimize sufficient but not necessary conditions, and the term that sometimes gets maximized by this minimization is actually an irreducible error. Like they're maximizing the discrepancy between the accurate, between what is now in representation space, the labeling function on source, and the labeling function on target. So you could think of it just as a picture like this. What they end up doing is they end up saying, in order to make them look the same, if I have different class balances, I have to like siphon off some of these guys and push them over there. And the reason why they think it's a good idea is, well, there's 2 things going on. One is that there's a little bit of sleight of hand in the way experimental results are reported. So we found these things are much less stable than they're reported. Sometimes, variance on errors aren't clear whether they're talking about standard deviation or variance, and makes a big difference when it's like 0.4 versus 0.016 or something. The other thing that's going on is they're actually always looking at uniform label distributions because they're looking at like MNIST versus SVHN, and nobody's thinking about what's the assumption that you're making, which is, I think, really, really dangerous. So and the other part of the problem is ill-specified, right? Like they're looking at distributions often that have different support. So anyway, you can see how things go wrong. We have a correction to the method that doesn't make it guaranteed to work, but at least makes it not guaranteed to fail in the obvious cases. And I think there's a lot more work to do here. So anyway, thanks so much for your time, and sorry for running a couple minutes